Hi, today let's solve a very common binary tree problem. Count the number of non-leaf nodes in a binary tree. A non-leaf node is simply a node that has at least one child. Let's take this example tree. We have 1, 2, 3, 4, and 5. As you can see here, nodes 4, 5, and 3 are leaf nodes because they have no children. Nodes 1 and 2 have at least one child, so they are the non-leaf nodes. So the final answer should be 2. So our logic is simple. If node is null, we ignore and we return 0. Okay, if the node has left and right child, it is a leaf, so we ignore it as well. Otherwise it is a non-leaf, so we count it. Okay, let's quickly look into the recursive approach. For every node we ask two simple questions: is it null and is it a leaf? If the answer is yes, then we simply return 0. Otherwise we count this node and recursively count left and right subtrees. So let's start from the bottom. We have node 4, it is a leaf, so we return 0. We have node 5, it is a leaf, so we return 0. Node 3 is a leaf as well, so we return 0. Node 2 has children, so it contributes 1. Node 1 has children as well, so it contributes 1. So therefore the total number of leaf nodes will be non-leaf nodes will be 2. So the core logic basically is, if root is equals to null, then we simply return 0. If it is a leaf node, we return 0. And if that's not the case, we simply return 1 plus left subtree result plus right subtree result. And notice that we traverse every node exactly once, and since we visit every node once, the time complexity will be big O of n, and recursion stack goes up to the height of the tree, so the space complexity will be big O of h. Now let's quickly go through the iterative approach as well. The idea is to traverse the tree level by level using a queue. For each node it has at least one child, then it is considered as a non-leaf node, right? So let's use the same tree and solve it iteratively. So we have 1, 2, 3, 4, and 5. For level order traversal, we use a queue. So we start with an empty queue and count is initialized to 0 first. Initially, we push the root into the queue. So the queue becomes this because we are pushing 1, which is the root of a tree, into the queue. So our first rule would be, if a node has at least one child, it is non-leaf, and we simply increment the count. Initially our queue would be, as we discussed, would be 1. So we simply pop 1, and since 1 has the children of 2 and 3, those 2 will be enqueued. So we pop 1 and 2 comma 3 will be enqueued, and we increment the count by 1 because it is not a leaf node. Now coming to node 2, we pop it and we increase the count by 2 because it is a non-leaf node as well. And 2 has 2 children, so we simply enqueue the children of 2 into the queue. So basically it becomes 3, 4, and 5. Okay, now we got to pop 3. Node 3 has no children, so it is a leaf node. So we cannot increment the count. So count will be 2 only. And now we pop 4. Pop 4. So actually the queue becomes like 4 and 5 when we pop 3. Now we are popping 4. So 4 is a leaf node. So we don't increment the counter here as well. Now we are left with 5. And the same goes with 5 as well. 5 is a leaf node, so we don't increment the count. The queue is empty in this case now because 5 is also popped up. Now the final answer will be 2 because the queue is empty, which means we end the traversal. So the total number of non-leaf nodes will be 2. This is a full iterative logic using breadth first search, and every node is visited once, so the time complexity will be big O of n. The queue can store nodes level wise, so space complexity will be big O of n as well. I personally prefer the recursive approach for clarity and simplicity, and I use the iterative approach when I want to avoid recursion stack overflow or when breadth first search traversal is explicitly required. Now let's look at the coding part for both the approaches. Let's quickly look into the recursive approach. We've defined the structure of a binary tree node, and we've also defined the function to count the non-leaf nodes are here. So let's first handle the base case. If the node is null or it is a leaf node, it cannot be a non-leaf node. So I return 0. That is, if root is none, for instance, we return 0. And also if root dot left is none and root dot right is none, we return 0. Okay, now on to the recursive case. If the node has at least one child, it is a non-leaf node. So I count it and we gotta recursively process its left and right subtrees. So we simply return 1 plus count non-leaf of root dot left plus count non-leaf of root dot right. Okay, that's it. Let's go ahead and run this code. As you can see the output for the first test case, we have two non-leaf nodes, so the output is 2. And for the second test case, for the single node tree, the output is 0 because a single node is always a leaf. And for the left skewed tree, which is the third test case, node 1 and 2 are non-leaf nodes. So here 1 and 2 are non-leaf nodes. So the output will be 2. And obviously for an empty tree, the output would be 0. So let's quickly look into the iterative approach as well. So basically, this particular recursive function, it counts nodes that have at least one child while ignoring the leaf and null nodes. So now let's go and code up the iterative approach. All right, let's quickly code this up using the iterative level order traversal using a queue. So I've defined a function that counts non-leaf nodes using an iterative approach. So first we'll have to look through the edge case that if the tree is empty, then there will be no non-leaf nodes. So if root is none, we simply return 0. Okay. And now we'll about the queue initialization. I initialize a queue and insert the root node for the level order traversing. So queue is initialized and root is sent to it. And we should also initialize a count which keeps track of the number of non-leaf nodes that we have in the tree. Now starting with the level order traversal, while queue, that is, I continue processing while queue is not empty, I need to remove the front element of the queue, that is node is queue.pop for the first element. So we are basically processing the first element in the queue. Now we need to check for the non-leaf condition, that is if node.left is not none or node.right is not none. I check if node has at least one child. If yes, it is a non-leaf node, so I basically have to increment the count by 1. So count is incremented by 1. And if a left child exists, I add it to the queue. That is, if node.left is not none, then simply queue.append node.left. Okay, similarly, if the right child exists, I need to add it to the queue. If node.right is not none, queue.append node.right. Okay. Now, after processing all the nodes, we can finally return the final count, that is return count. Okay. Let's run the code. As you can see, for the same test cases, we got the same result for the recursive approach and the iterative approach. So this solution uses breadth first search and counts every node that has at least one child. Thanks for watching.